All right, so, ladies and gentlemen, today we've now just observed 9 different demonstrations, okay, all of which relate to Newton's 3 laws of motion. As I said earlier, we kind of use that to kind of build up our more mature understanding of Newton's laws of motion. So now let's go ahead and let's put it formally together. Okay? Newton's first law of motion. Okay? It is helpful for us to understand, in this case, the development of a concept. Think about the year 1600. It's more than a couple of years ago. Scientists believed that the natural state of matter was for something to be at rest. And if something was not at rest, there had to be something continually happening to it to keep it in motion. Okay? Think about the time frame we're talking about here. We didn't have any expansive scientific equipment. Anything that needed to be used equipment-wise needed to be made. So we didn't really have a whole lot of discovery until about the 1600s. And it was until Galileo came along that gave us something that was a little bit different. Okay? So this was in the 1600s. Okay? He was the first scientist to think differently. Okay? And he believed it is the nature of the object to resist a change in motion. And understand the difference between that. Okay? That means that whatever motion it has, it is going to want to resist changing that motion. So that also incorporates something that is potentially moving. His word specifically, any velocity once imparted to a moving body will be rigidly maintained as long as the external causes of retardation are removed. Now, let's be adults about this, but more specifically, what is he talking about with the external causes of retardation? Very specific forces for the most part. Friction is a large part of it. Okay? So long as we have friction taken account for, or any other force that is working against that motion, okay, that something that is moving is going to continue moving, and with a velocity that remains the same. Even though Galileo is the one that really put it together, Newton is the one that gets credit for it. Why? Newton gave it a name. Okay? And Newton called it his law of inertia. Okay? So with the law of inertia, he said, and this is kind of the way in which I want you to understand it, because it incorporates all the pieces, in the absence of external forces, an object at rest remains at rest, and an object in motion remains in motion with a constant velocity. Please do me a favor. Underline, highlight, tattoo it on your forearm, with a constant velocity. That is a very important piece of Newton's first law. It's not just that it's going to move. It's going to move in a very specific way. And any change in velocity must be a result of external forces. Now, I know in our demonstration for second law, we started talking about external forces. It also comes up here. But object at rest remains at rest in the absence of external forces, and an object in motion continues in motion with a constant velocity in the absence of external forces. Okay, inertia, the term that Newton himself created. Okay, it is the tendency of an object to resist changes in its velocity, and it simply is a measurement of the object's mass. Okay, so if we have an object that has more mass, it's going to want to resist a change in its motion more than an object that has less mass. So up on the board very quickly, we have just a quick thought experiment for us. We have a Suburban and a Porsche that's sitting at a stoplight, two very different massed vehicles. Okay? They're sitting at the stoplight and the light turns green. Which vehicle requires more force to get up to whatever speed they would travel? The Suburban, the larger SUV. It's going to require a lot more force to get up and going. Why? It has more inertia. It requires more force to overcome the inertia that it has. It wants to stay at rest because that's how it started. Now, in the same regard, let's say those two vehicles are now going at the same speed, and then they're going to be approaching a stoplight. which one is going to require more force to stop? The Suburban is also going to require more force to stop because it has more inertia. Once it's up and going, it is going to require a lot more force to bring that to rest. So understand that not just with vehicles, but anything, okay, any object that has more mass is going to want to resist changing its rest, or an object that is moving will want to continue in motion at a constant velocity. Good. Okay, so let's go ahead and let's get on to Newton's second law. And by the way, I think we already answered this, even though it kind of is in your notes. What is a force? We talked about it earlier. Any push or pull on an object. Okay? And I know we kind of brought that into the fray when we started talking about Newton's first law, comes to the second law, also comes to the third law. Okay, so Newton's second law of motion states the acceleration of an object is directly proportional to the net external force acting on it and inversely proportional to its mass. Now here, Newton was able to kind of pull together all the relationships between all three. So acceleration is directly proportional to the net external force. The direct proportional means as one increases, the other increases by the same amount. So, if we double the force, the net external force acting on an object, what should happen to the acceleration? I'll say it again. Listen carefully. If the net external force doubles on an object, what would happen to its acceleration? It would also double. That is the direct proportionality between those two. Inversely proportional to its mass. Okay? So, if we were to keep the force constant, but let's just say we double the mass, it's going to give us half of the acceleration. And that's what the inverse proportional is. So whatever's happening to one, we would take the inverse of that, and that would help us to figure out what's going on with the other. Now, down below, okay, you see the two ways in which Newton's second law can be stated mathematically. What is that funny little letter that is sitting in front of the F? It is the Greek letter sigma. And mathematically speaking, what does that mean? It means the sum. Okay? So one of the things that we have to do in Newton's second law is we have to be able to focus on all of the external forces acting on an object. We do not just focus on one at a time. Okay? We have to figure out what is the net effect of all of the forces acting on, all the external forces acting on that object. Okay? The EXT is just a designation to remind us that we have to have external forces. Internal forces do not affect acceleration at all. Okay, very quick before we go to the next slide, actually two things. You see I have handwritten out to the side kind of the rearranged version for force. So we get net force equals, because we often will use it as that as well. You at some point have probably heard of the kindergarten version of this, which is just simply F equals mn. Okay? It is more than that though. It's not just one force, it's the net effect of all of the forces, and we now also know that they have to be external forces as well. Real quick, let's talk about units. Okay, acceleration is the one that we already know because we have used that in previous units. What are our units, or SI units, for acceleration? Meters per second squared. Okay, so we know that. Awesome. Okay, mass. What is the SI unit for mass? It is the kilogram. And it is my job as your physics teacher to tell you that your chemistry teachers lied to you. Why? Because they're lazy. Now, of course, that's a little bit tongue-in-cheek. There is a reason why chemistry treats mass in grams. One, in chemistry, for most of the stuff you do, mass is all relative. Okay, so no matter what scale you set it in, it'll work with whatever, as long as your units work through whatever equation you're trying to use for that. In addition to that, let's say you're actually doing some sort of reaction and you have a measured amount of something. If you were to try and express everything in kilograms, everything is going to be very, very small numbers. Okay? So it is much easier to mass out 40 grams of a substance than it would be to be 0.040 kilograms of whatever it is that you have. Okay, so that's why often in chemistry they do that in grams. But you should know the SI unit for mass is the kilogram. And if we need to do conversions, which we'll have those, we'll be converting between grams and kilograms for some of the stuff that we have going on. Now, force. Force is the one thing that we don't have a unit for yet. But take a look at my handwritten equation for a minute, because it's actually going to lead us to the derived unit that we're going to see on our next slide. We said our units for mass is what? Kilograms. If we were to take that from a unit analysis standpoint, that would be kilograms times the units for acceleration, which would be meters per second squared. So technically, the units are kilograms times meters per second squared. But we decided in physics that that was going to be a little cumbersome every time we wanted to go ahead and express a unit of force, especially in the SI unit system. So in the SI unit system, we truncate that to a Newton, abbreviated as a capital N. What is 1 Newton? It is the force that you would have if you took 1 kilogram of mass and accelerated it at 1 meter per second squared. Earlier in class, you had an opportunity to hold 1 kilogram of mass in your hand. Okay? If you can kind of think, what kind of push or pull would I have to put on that to get it to continue to accelerate at 1 meter per second squared? That's what 1 Newton of force would be. Good so far? Okay, one last little thing, and this is related to some of the stuff we were talking about earlier. I was a real stickler for trying to describe things in a proper way, and you didn't know why until right now. There are things called gravitational forces, and there are things called the acceleration due to gravity, and they are two separate quantities. Okay? Now, you see some notation on the board that we're going to explain a little bit more next class, but the F with the subscript of lowercase g is my way of designating weight. A weight is a force. It is different than mass, for reasons we'll see a little bit later. Okay? I do need to put a disclaimer out there. Once we start labeling forces, this is one of the things in physics land that varies wildly depending on who's doing it. Some people might use other labels for forces. You look something up in a textbook, you go to Khan Academy, you go to something else different, you might see things expressed a little differently, and that's okay. It's just one of those things that we have different labels depending on what it is we're doing. I have my method for a reason, and we'll see that a little bit more next class. So anyway, F with lowercase g as a subscript is the way that we will represent an object's weight. It is equal to the object's mass in kilograms multiplied by g, which if you follow the terms that I've been using, what does g stand for? It's not gravity. It is the acceleration due to gravity. And if you were to kind of take a half step away from that equation, isn't that still just Newton's second law? Okay? If the only thing we have is the acceleration due to gravity acting on a mass of an object, that's going to help us provide what that object's weight is going to be. So this is purely a function of Newton's second law. So when we go to find an object's weight, of which we'll be doing very soon, okay, we will use an application of second law. But again, just drawing attention to the fact, okay, we have the gravitational force, or the object's weight, and we have the acceleration due to gravity. Okay, Newton's third law is the one that is easy to kind of state, but to kind of understand what we have going on below, it's not complicated, but it just takes a little bit of adjustment of what we're thinking about. Newton's third law of motion states that for every action force, there is an equal and opposite reaction force. Emphasis on force. Third law only deals with force. It does not deal with acceleration. It does not deal with mass. It does not deal with velocity. We're solely talking about the interaction between two forces. Ultimately, two objects interacting. Now, this technically is an equation, but this is also our start into understanding a little bit of notation that we're going to use with forces. Okay? I'm going to read to you in words what that equation is at the bottom. And I'd like you to follow along with me so we can understand. The force 1, 2, not F12. The force 1, 2 is equal to and opposite in direction to force 2, 1. Does everybody see the equals negative piece of that now? The two forces are equal and they point in opposite directions. Now, what is 1, 2 and 2, 1 mean? Here's how I do that. Okay? F12 is the force on object 1 as a result of object 2. F21 is the force on object 2 as a result of object 1. So earlier, when Ziad and I were having our push of war, doesn't matter what we call 1 or 2, okay? But the force on one force plate as a result of someone pushing on it is going to be equal to the force on the other force plate as a result of the other individual pushing on it. Okay? That's what that designation is. It's not always done using numbers. A little bit later in the year, we actually use letters sometimes to kind of designate the interaction between multiple objects. We're not limited to that, but it's the force, the way I frame it, the force on the first identifier as a result of the second identifier. Okay, Newton's third law is all about action and reaction force pairs. Understand that we are specifically referencing the force interaction between two objects. Now, I hope you can forgive me, but I could not find a scale drawing of the situation I wanted to portray, which is simply a soccer ball sitting on a table, sitting somewhere on the earth. Not a scale drawing. Got it? Okay. So let's focus on the force interaction between the soccer ball and the table. Does the soccer ball push down on the table? Absolutely. With a force equivalent to its weight, as we will find out. And let's just say, for mental math purposes, let's say it has a weight of 10 newtons. That means there's 10 newtons of force pushing down onto the table. Does the table push back up on the soccer ball? Absolutely. With what quantity of force does the table push back up on the soccer ball? 10 newtons of force pushing back in the opposite direction. So those would be the action and reaction force pairs. The action is the weight of the soccer ball pushing down, because if that's not there, the table's not going to push back. Okay? The reactive force is going to be the table pushing back up. Okay? Now, let's focus on the interaction between the table and the earth. Does the table push down onto the earth? Yes. With an equivalent force of the combined weights of the soccer ball and the table pushing down onto the earth. So if we just make up, let's say it's 100 Newton weight for the table and 10 newtons for the soccer ball, how much is our force that's pushing down onto the earth? 110 newtons, correct? With what quantity of force is the earth going to then push back up onto the table? 110 newtons. So you're kind of seeing how that works. All right, one last thing in our notes that's going to kind of springboard us into what is going to be due for next class. Okay? I want to take some thought experiments because these are real life situations that we describe using Newton's laws of motion. Okay? So, using Newton's second law, we need to explain why a rocket accelerates if the force it produces is constant. Okay? And I guess we're talking from the moment the rocket is already ignited to the point where, right to the point where it uses up and consumes its fuel. If it applies a constant force on the rocket, why does it accelerate? And I guess something else to consider. Is there a gravitational force that's pulling the rocket back down to Earth? Is there a gravitational force that is pulling this rocket back down to Earth? Yes. So what does the rocket have to do in order to accelerate it upwards? It needs to be a force that is greater than that gravitational force. Okay? It still is a constant force. It doesn't change the amount of force while it is ignited. Okay? But it needs to be greater than that. Now, I do need to state, using Newton's second law, if even it was only 1 Newton greater, it is going to accelerate, but at a very, very, very small rate. And then your rocket's not going to really go anywhere. Okay? It needs to greatly overcome that. Because for a rocket specifically to get to outer space, it actually has to attain a very certain speed to even have the ability to escape Earth's atmosphere. Okay? So that's the first part of it. Now, the last one, I actually love this as an example because if you think about it, it is actually a very complex problem with a very simple solution. Okay? Using Newton's third law, explain how a rocket is able to move through a vacuum like space. Here's the really complicated problem. Once you get to outer space, there is no particulate matter for you to push on. How do you then move? There's nothing to push back on. Think about that from, we kind of talked about it with our remote-controlled truck driving on a sheet of ice. If there was no reactive force in that regard, how does it move? Because we know that things do move. You have to be able to slightly alter your trajectory and do other things to get there. So how? There's no air there. You create the particulate matter of which you push on. Okay? Have you ever seen, whether it's through science fiction or whether it's somewhat genuine science, anything that's in outer space with little microbursts, it'll kind of, it is creating its own particulate matter to push off of. Because as it is, there's nothing that's there. So that was kind of one of the challenges of traveling through spaces. We need to be able to have something that is able to make those adjustments. Because, you know, it's not like we're just here on the surface of the Earth or an airplane flying through our atmosphere where we can change the way the air moves to alter our trajectories. They have to figure out a way to go ahead and do that. So, good. Okay, that's what we have for our notes for today.